Do Jackass videos still exist? Must do, right? Do they still made anew?
And this is the fire video. I'm Dave England, and this is the Fire Hose Rodeo.
So, why isn't the sound coming through? I wish it would. Seems that all I have to do is open up settings and it automatically sets it without me doing anything, but it won't do it on its own. Okay, no it doesn't, so that should work. Now, let's start this class properly. What? Oh. The Vuelta a España. Well, I guess you saw that video, so perhaps we don't need to watch it again. I think it's a funny video. Well, we'll watch it again. So let's do some other stuff, which is just as relevant. So I'm at a loss as to why we don't have volume, but I don't really care.
Or personal propulsion device can reach top speeds of a little over 40 miles per hour, reach an altitude of about 50 feet. Unlike other jetpacks, this one can keep its pilot aloft for hours and fly for about 186 miles.
Job interview.
Is that this one leaves its fuel supply
Job interview.
and power plants on the ground, or more appropriately on the water. That's it there, floating in a little pod on the right. A four-stroke power plant.
Yeah, I walked past it yesterday.
Can range from 130 to 300 horsepower, is housed along with the fuel to run it in a floating mini boat. That floating power pack is tethered to the jetpack by a long hose that delivers pressurized water to the control nozzles. The pilot has pitch control of the nozzles and a twist handle to control power. Unveiled at the Dusseldorf Boat Show in
Dusseldorf.
sport aircraft, the company says it's already seen interest, and the training to fly the maneuverable pack is included in the price.
Yeah, interesting. The jet. Sorry?
Did you ever invest in one of these?
Oh, was it 30K? No. I drive a 20-year-old Jeep that cost me $7,000 10 years ago. No. So, yeah, well, I don't know. It's interesting. I think it's 2007. So it's 18 years, I guess. And it's not a very cool one. It's a Liberty. I used to had a Cherokee before with 250,000 miles on it. We're returning back to San Francisco. San Francisco International, not so far away from our balloon boys.
Perhaps there is none more dangerous than that of a jet engine. The danger exists on both ends. It sucks up what's in its path and blows away anything behind it. If it's powerful enough to throw a 435-ton airplane into the sky, imagine what it could do to you or anything else near it. Some don't realize its power. Many don't think it can hurt them. This stage demonstration will show you what it can do, and a picture is worth 1,000 words.
Definitely San Francisco. I'm glad it's staged. So, yeah. So, interesting. I didn't know Is that the last one or something else? Oh yeah, fine. Other stuff as well. Just to whet your appetite. I think this must be the America's Cup. Used to be that America's Cups were yachts, sailboats. Now they're catamarans, and specifically catamarans that have hydrofoils on the bottom as airplane wings, which lift the boat out of the sea. So you're kind of up on stilts on these hydrofoils, and they go much faster, probably twice the speed, I think. They must be going 60 kilometers an hour or something. Perhaps, actually it says, no, 30 kilometers. Oh, that's 30 kilometers to go, perhaps. So anyway. So some examples of what we would like to understand as I guess I could leave that on and just put the volume off. Some examples of what we'd like to do now that we're moving to fluid dynamics. So the first 3 weeks, we've talked about fluid statics. I guess I did send an email. I sent it on Monday night, so there'd be no confusion that it was next week, week 5. So you have that. You have all the materials online. Any questions about that before we move on? It's pretty self-explanatory. I'll repeat, the questions are verbatim, with things changed from the previous stack of questions you have. So that might inform your review for this. Okay. So we'll start talking about fluid dynamics today. 4.1 was the last statics part, even though they're accelerating fluids. And actually it's a segue into the material that we need to deal with this. Maybe as usual, maybe we go through a quick recap on what we talked about last time to make sure everything's in everyone's minds before we head out on our new adventure as this begins. So we're in 4.2, so that's where we are. What do we talk about? So far, this is what we talked about on Friday, it's Friday. And that was that pressures change with elevation with unit weight. I guess we also had the fact that if you accelerate, I won't write it there, if you're accelerating upwards, then dp dz equals rho g plus az, as opposed to this. This is a static fluid that's not accelerating. This is a static fluid that's accelerating in the z direction. And so it's useful, bless you. And I'll just briefly talk about our tank example. And so if you start off with a tank full of fluid and you accelerate it in the y direction, actually this I guess would be y here, then the fluid, if it's a positive acceleration, you could imagine it's like bulldozing a fluid on the beach. It kind of stacks up at the back of the tank. This area volume here matches this volume. It rotates. This has an inclination that's given by dz dy. And the expression that gives that is this. It's got a negative sign on it. The question was why? Because things have gradients. A gradient that goes down in this direction in this quadrant is a negative gradient. This is a positive gradient. And so that's reflected. I guess you can show that by going from one point to another. So if you go from this point to this point, you have to go up positive z, and you have to go across negative y. So this is a negative minus VE gradient. Z, y. And we talked about this. Standard result. If it's accelerating upwards, in addition to going horizontally, then the pressure distribution is given by this. If it's not, if acceleration is 0, AZ equals 0, then it would just be rho GH. This means that it's going, your fish tank is going up in an elevator as well as driving along the road. If the acceleration Z is positive, which means it's going upwards, then the pressures would be increased by this amount. G is always acting downwards, but it's always positive. AZ is acting in the positive Z direction, which is upwards. And if it was, so this is AZ greater than 0, and this would be AZ less than 0. And so that's perhaps useful to go to. So that should explain everything you need in your near future. We talked about rotating fluids as well. I'm not going to go through that here, perhaps just because I almost can't help myself, right? Just to make the point that it's very similar. Here you rotate about an axis. This is Z. It's rotating in some direction. Doesn't matter if it's clockwise or counterclockwise. And as a result of that, you get some free surface developing, which looks like that. Well, it's not bad. And so it changes relative to the center line, different from being a pressure. This is the surface of this being a linear surface, right? This is dz dy is linear. In this particular case, dz dy is not linear. It varies with the square of the radius out from here. And so we talked last time very briefly that if you want to figure out what the location of this is, you have to solve for the value of the constant and then move. I imagine there might be a question in your homework on that, but I guess that won't be till next week. Homework's next week because the test will be due on the Sunday rather than the Thursday, right? As well. So don't say I don't have a heart. So that's it. Questions? Yeah.
So, in all of these sort of questions, we're always assuming that there's enough gap, there's enough internal space for the fluid.
Yeah. So at some magnitude, it would slosh over the back of the tank, right? And so a question could be, what's the maximum acceleration this truck full of water could take before it goes over the back? That has been a question in the past. Yeah. So the plus and minus are equivalent, and the maximum height you could get would be on the back side would be this. So you'd know what the maximum slope could be, so you'd calculate the acceleration from that. That's not a question this year. But okay. Good. All right. Fluid dynamics. That's what we're starting. So what we're interested in is, let me define what we're going to look at. We're going to look at Bernoulli's equation. I'm guessing that probably you've had some contact with that in your past. Whoops. So this is the idea, I guess. Oops. If I stop, then it draws a straight line. So we would define streamlines around a structure. And we could imagine that on each of these streamlines, we have a packet of water. And so fluid mechanics isn't any different from your dynamics class, where you use F equals ma. That's what we've used so far. And so you could think of it as a packet of water in a differential cube that scoots along this streamline, and we want to be able to balance the forces on that to be able to see what the flow regime would be like and to be able to see what the pressures would be that are acting in this flow relative to this system. The final result that we will get will look something like, which you've seen before, and I always use it in this form, is that perhaps I should draw my coordinate system. So we're going to look at this. We're going to define this as z1. We'd have this as a velocity v1. You notice my lowercase v's don't have a bar through them. Uppercase V is always for volume. And we would have a pressure P over gamma. This is P1. And we'd have a downstream point, which I'll put here. We could also think about a little cube of fluid that's around it. This has a velocity along the streamline called V2. This has some pressure, which we'll talk about, which we'll define as a pressure head, as a length. Pressure 2 divided by unit weight, and a pressure, or an elevation, Z2. Z2 is always positive upwards, as we've said, or Z is positive upwards. And the converse down. And so you'll know that Bernoulli, probably, Daniel Bernoulli, is that, bless you, that's my job to say that, is equal to the elevation head. I'll write them as I over unit weight plus VI squared over 2G equals constant. And so if you write it here for location 1, then you have 3 terms. If you write it here for location 2, you have another 3 terms. They have to be equal to each other. And so if you only have one unknown between these 2 things, then you can solve the equation. You can solve for the pressure that's around it. You might want to know what the pressure is above a wing to know what its lift is. As it would be a typical thing that you'd like to know, for instance. So you could see whether your airplane can take off, or you might like to see whether the pressure that's acting on the side of the truck that's being pulled along SFO is big enough to roll it off the runway. And we can calculate that. We'll do an example like that. So that's the basic, that's the end point of this. So we can certainly look along a streamline, which is what we're doing here, which we'll call, in the book they call it a vector, but we can also look in the normal direction to that. And so that's what this is. We're mainly interested in the behavior along a streamline, in which case Bernoulli looks like this, but we can also write it normal to a streamline. And if this was a liquid, for instance, and if this was a free surface, then actually the pressure distribution, even though it's flowing, would look something like we've seen in the past. It would just be the weight of the fluid above it, even though it's moving across the system. Well, we did that already, right? For the aquarium moving across the room, that's a static problem. It develops pressures in it that are varying linearly with depth. And so there's no reason why in this little differential cube that we're moving down that we wouldn't also have pressures varying as a function of that. So that's what we are trying to look at. So let's figure out exactly what that means in terms of what we know already. So we'll look mainly at this. I don't think today we'll look at normal to a streamline. But let's take our little differential control volume. And let's let that move through a couple locations. And we'll call this location 1, and we'll call this location 2. A bit like these 2 points here, but it's just in the vertical direction. If we're having it flow horizontally above an airfoil, we can equally do this vertically. And if we do that, we can use our previous expression. You remember this from last time. Is it negative dp dz minus rho g minus rho az equals 0. And I'll just remind you that we can't do it today, but this is this expression that we've been playing with. We drew the little box, this little box. This is it here. All I've done is moved this equation here and set this equal to 0. So we've seen this before. And it comes just from us resolving forces on that little differential cube, which could be just a bucket of water that's moving. It's just, as I say, everything in fluid mechanics is the same as just dynamics. You can think of filling a balloon with water, and that's the unit that we're moving around, and it will be represented by this. Beer? Red Bull to get you through the morning? So, what's acceleration? Acceleration is dv z dt. It is also, if we multiply by 1, this, which is also dv z dz times dz dt. So dc dt, if you attach it onto me, z is going upwards, and the time it takes to travel is a velocity, right? This is a velocity. This is actually vz. And so this is actually equal to vz times change in velocity in the z direction with space, right? And that is also equal to a half d v squared dz as a standard result, right? This is. And you can show that that's the case, right? Because you can multiply this by dv over dv. Perhaps I don't want to do that. If we multiply this by dv over dv, then we get a half dv over dt times dv squared dv rather. Differential of this is 2v, so it's a half times 2v times dv dt, which is dv dz rather. Right? All I'm doing is showing that this thing that I pulled out of the box is actually equal to this. So this is what we call convective acceleration. And all it's doing is it's saying that if I run across the room, I have an acceleration which would be my change in velocity with time attached to me. But what we'd like to do instead of which is how we have to use F equals ma, but we'd like to be able to calculate that expression not from being able having something attached to me that measures my acceleration, but being able to look at my velocity here, my higher velocity here, and use those two velocities in space to be able to calculate what the acceleration dv dt is. So that's exactly what this is, right? This is an acceleration of me as a function of my velocity at any point multiplied by how my velocity changes with space, not with time, right? And so we're going to use that here. So if we would use this, then we can substitute it back in here. I'm just going to write out this upper expression again because I can. Rho g minus rho times acceleration. I'm going to write it as equal to a half d v squared And you just need to know what this is. So if this is confusing, don't worry about it. dz, which is this, equals 0. And actually what I will do also is I will write down through here the fact that 0, not a very good 0, 0 is equal to this is F equals ma, written differently. This term here is the inertial term. Me being accelerated across the room, or a packet of water being accelerated across the room, requires a force to move it or to decelerate it. And so that's the inertia behavior. And these are the other pressures that are acting on the system. The fluid pressure and also the body weight of the fluid as it goes down the system. So what else am I going to do? So it's just F equals ma. And actually, if you divide this by a volume, and this by a volume, kilograms per unit volume is density. And so these expressions are in terms of force per unit volume. So in other words, you have a cube of water, dx, dy, dz. The force per unit volume of that, the volume is dx, dy, dz, added, multiplied together. And so that's the forces that we're applying. So what we're going to do is we're going to multiply by dz, dz, dz. We're going to divide by unit weight. And if we do that, we end up with minus dp over gamma minus rho g dz over rho g minus, this is a density, right? Rho over rho g times a half times d v squared. Don't worry, your torture will be over soon. dz equals 0. And so if we integrate this, then what we get out of it is minus p over gamma minus z minus v squared over 2g. And since we're integrating, if you don't integrate between 0.1 and 0.2, you just integrate generally, you end up with a constant on the right-hand side, right, instead of this. So, Bob's your uncle. That's Bernoulli. And so that's exactly as this, same as this expression here. So that's where it comes from. So all we're doing is we're taking the same expressions we had before. Don't need to derive this, but it's useful to know where it comes from. It comes from the fact that we're taking a little cube of fluid, we're allowing that to flow down a streamline, and as it flows down a streamline, it may accelerate or decelerate, and we can account for that, and we can account for it in these terms. This is the term that accounts for the deceleration or acceleration. It's the convective acceleration, as we've called it. It's not dv dt, but it's acceleration in space between 2 points. And this is the pressure that's present in the fluid, and this is the elevation it finds itself at. So this is potential energy that's being converted to kinetic energy. So potential energy to kinetic energy, because one is exchanged for the other. The pressure that it acts at in atmosphere wouldn't count. So that's really all we're dealing with. And so we use Bernoulli's equation, and we characterize it along a streamline. There are some conditions that have to be met for Bernoulli, and I'll write them below. So, and of course you can turn these to positives, right? And so requirements. See if I can remember them. One is it's inviscid. So the viscosity equals 0, has to equal 0. That's not true for any fluid, but it'd be good if it was close to 0. It tends to work for lots of cases where it's not completely true. It should be incompressible. And so that would be that it's, what did we call it? Its compressibility should go to 0. Or its bulk modulus should go to infinity. One is the reciprocal of the other. And so an incompressible thing is something that doesn't compress, so it'd be brake fluid, or water is actually incompressible if you put it in a container. Air is not, but actually we'll use Bernoulli for the forces above airfoils, and it'll work just fine. 3 is irrotational. So it means that as it's flowing downstream, it doesn't get into eddies as it goes downstream. So in other words, sometimes if you have an airfoil that you're blowing past, when it comes off the back end, it makes these little eddies, just like eddies in a stream. And these are vortices, and they're rotations. And so it doesn't work well if the flow is rotational. So you don't want this, I guess. And you don't want this. Or I guess these are the conditions when it works. And the 4th is steady state. And so what steady state would mean would be for our airfoil, whoops. Steady state would be that if you look at this wing now, and if you look at it 10 minutes later, the flow pattern would be the same. It hasn't changed. But of course, you know, the particle of air, the molecule of air that was here 10 minutes ago would be somewhere else after 10 minutes. And so it's steady state relative to the observer. And of course, if you think of this wing and the plane was going past you and you're static, so it's on the runway, the plane's going past you, you'd see the air at one point where it's ahead of the wing, then you'd see the wing come past you and there'd be air above it, and then it'd go past you. And that same location would have 3 different velocities as the wing passed next to it. And so that would not be steady state, but you'd have to choose your reference frame to be steady state, right? So you can choose your reference frame by sitting in the plane and seeing everything rotate next to you. So those are the 3 requirements for Bernoulli that we need. Okay? Right? All right, so let's do an example. Yeah.
What this means, or just beyond just the mathematics?
It means that your fluid is not treacle or molasses, but it is air that has low viscosity. So water has a viscosity of 10 to the minus 3 Pascal seconds. Air is about 2 orders of magnitude less viscous. And yeah, so air versus molasses. And yeah, okay. Okay, right. Hopefully everyone saw our movie as you came in. Let's see how well I can draw a jet engine. Actually, before I'll start this, but I'll go to something else. I'm going to come back to that. Yeah, blah, blah. So you see all these things, blah, 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 blah. Lots of math. We've done this. Oh, God. I must be your hero. Because we don't need any of that. So yeah, let's do this one first, actually. This is more telling. So this is just flow down downrange. And it's kind of what we've drawn already, that if we looked at the pressure at this point here, pressure in a stream would be given by the elevation head. The stream surface would be here. If you looked at the pressure below this, it would look like this little pressure triangle. And there'd also be an extra term here that would relate to the fact that this point, the fluid here, has some velocity v1. And so there's a velocity head which gives you what we'll call this an energy grade line, EGL, energy grade line, which means that this energy is constant as you go downstream. So actually the fact that the viscosity is 0 means that this line can be constant, because if viscosity is not 0, then it dissipates energy. It means that as it flows down a pipe, it loses velocity because you're using up energy, you're dissipating energy as heat. And so the fact that mu equals 0 allows this line, the energy grade line, to be horizontal, which is the definition required in the definition of Bernoulli. If you put a little tube in here that points upstream, which is actually the same as the pitot tube that exists on the side of a plane, which measures airspeed, then the fluid would stagnate at this point. So at this point here, specifically, I guess I don't need to do that, V is equal to 0 because it gets killed, because it's trying to enter into this tube, but it can't because the tube is open to the top, but once it's full of water, it can't do anything. And so what it would do is it would kill the velocity that you have here, V1, to being V2. So this is perhaps V2 equals 0. So on the same streamline. And what it would do, it would convert the pressure from being just equal to this head here. This would now be the pressure head. This would be P2 over rho g. And you asked before, why do we care? Why do we measure pressure? Here, we'd like to measure pressure because we could use this to calculate exactly what V2 is, or V1 is. We know what V2 is, so we could calculate, if we measure this pressure, exactly what V1 is, which is how a pitot tube works, and it's why you have it on a plane. And as you go downstream, you get the same behavior. So this is the essence of Bernoulli. Energy grade line says that Bernoulli elevation head plus pressure head plus velocity head upstream, when added together, equals those three components downstream. The graphical representation is of these lengths. Length, 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 dimensionally homogeneous, adding oranges to oranges, not mixing things, as we talked about dimensional analysis. That's it. I always often write it in terms of a length, just easier. Some people like to write it in terms of different components, pressures. You can write it any way you want just by dividing through the whole thing. So one illustration of that is this one as well. So this, let's think about our elevation head, our pressure head, and our velocity head. And look at each of these values for this thing. So you've got a syringe, you fill it with water, you pop it into the air. And so we're saying that when you add these together, I guess, if you add these together, the constant. And so what would these values be as we look at these points? At point 1 here. Well, Z would be low. V squared over 2G. It's fluid that's in a reservoir. The reservoir is not flowing, so the fluid velocity would also be low. But the pressure in a bike pump or in a syringe is going to be high. That's not E. And so if you add these together, whatever the numerical values are, you'd end up with some number, I guess A. You go to point 2. Elevation, medium. Pressure, it's in the atmosphere. It's already come out of the atmosphere. We know that the pressure in the atmosphere acts in all directions and is the same. So the pressure acting horizontally has to be the pressure acting vertically, and that's very low. It's going to be atmospheric, so much lower than it was before. And the velocity is going to be high. If you add those together, you get B. And then it'll keep on going up. It'll get to the top of its arc. And so the elevation here will be high. The pressure will also be low because it's in the atmosphere. And the velocity will also be low. And these have to equal each other, right? If you had numerical numbers for them. That's just an illustration. So that's just an illustration of exactly this case, that the energy grade line, that the energy that this particle, this is actually a streamline, right? And we use S for streamlines, not Z. And so the other thing, I guess, is that we're measuring these things. We did do it in the Z direction, but we can also do it along a streamline. So a streamline in this case would be this green thing here. And so it's along this streamline that we're measuring these things. Otherwise, it's not useful to us if we can only do it in the Z direction, right? So Bernoulli applies along a streamline, not normal to it. Good? Yes?
Reminder, what does DATUM mean?
Say it again.
DATUM. I'm not
Datum. Latin for the beginning, perhaps. No, measuring location. Yeah, datum. You say datum, right? It's country. But just like verbatim is Latin, I think. Okay. Not Latin class. Did any of you learn Latin in school? Oh, you're lucky. Okay. Let's go back to our tarmac example. You can look at the video if you came in later. And so this is the example. So we're going to write Bernoulli at 2 locations. We're going to write it here, at location 1. We're going to have a streamline that does this, that stagnates and goes around our thing. And we want to define it here, point 2. Actually, the behavior just before point 2, this is called a stagnation point. Where it goes from a velocity which is positive along the streamline to 0 velocity where it stops. And so what we can do is we can write the conditions for Bernoulli along this point. Okay. So this is X, this is Z. So Z, P over gamma, V1. Let me not write, let me just write the terms, not. So this is P1, Z1, V1. And so this is 0. Let's just choose our datum to be 0. And we can write it over here at point 2 as well. So this would be Z2, P2, and V2. So it comes out of the back of the jet engine. We know that if we choose our datum at this level here, so this is our datum, which is Z equals 0, then that's goes across. Pressure, atmospheric, as we said before. The pressure acting in all directions in the atmosphere has to be 0, one of our standard results. And if we take gauge pressure at 0, then that's the case. And the velocity is equal to 200 miles an hour. I think planes take off at 120 or something miles an hour, which is equal to 100 meters a second, roughly. Z2, 0. This is in meters. This would be in pascals. Pressure at 2. Big, right? If it blows a truck off the side of an apron of an airport, it's big. And the velocity is equal to 0, and that's in meters a second. And so what we can do is we can write Bernoulli between upstream and downstream. Which takes a time for me to write, and equate them. We only end up using 2 of the terms. And if we throw the terms away, we know that Z1 and Z2 cancel. We've chosen to be 0. We know that the pressure here is 0. We know what this is. We don't know what this is, but we know that this is equal to 0 from these terms here. So we just have the equation that, if I write it backwards, P2 is equal to unit weight of the fluid times V1 squared over 2G. And so we could calculate what that is. So V1 squared is 10 to the 2 meters a second all squared times 10 to the 4. Actually, we can make life easier, can't we? We can get rid of this and substitute it as rho g, in which case we get rid of g and we get rid of g. So this now is just rho. So rho is equal to 1,000, no, much easier. It's air, 1 kilogram per meter cubed, roughly. And that's divided through by 2. And so P2 is equal to 10 to the 2 squared is 4, is 0.5 times 10 to the 4. If you go through it and realize that 1 kilogram accelerated at 1 meter per second is equal to 1 Newton, then this is newtons per meter squared. Hopefully. Which is 5 times 10 to the 3. Pascals. So what else do we know about this system? We want to know whether the thing falls over or not. So we want to know what the force is acting on this truck. And so we can make some simplifying assumptions. I'm going to make the truck a non-standard Ford in terms of metric system. So let's say that, I want to write this. So we have a pressure acting here, which is equal to P2. What's the distribution of pressure on this surface? Is it going to be this? I think so. And so the force acting, which I'll call maybe uppercase P, is going to be is equal to P2 times the area. Area into the page, right? So this is the side of the truck. I don't mean to be pedantic. Some of you find this very simple. And for this truck, 3 meters squared. Roughly, right? 3 feet by 10 feet long, side of a truck, roughly. Why is it this uniform distribution? Well, because it's killing the motion of a particle everywhere along here. So this would be acting here. Why doesn't it have a triangular distribution? Well, it does, but the triangular distribution is due to the unit weight of air. And it's so trivial that we're not going to care about it, right? So this would just be a flat distribution. So what we'd like to do is we'd be able to resolve forces. These are the wheels at which it's sitting on. Has a weight of a truck which will act in the middle. A truck is probably 6 feet wide. So this is 1 meter, and this is 1 meter. And this is so the other thing that I guess we'd know here, if this is a uniform distribution, we know that it acts through the centroid. If it's got a linear, the varying with depth distribution, it's a 2/3 below the height, but this doesn't matter, so this is just acting at half height. So this is acting, I'm going to say that with these being the tires, that it's acting at a height of 1 meter, just because it's easier. It's about right. And I'm going to call this LP, and I'm going to call this LW, right? So we can take moments about this downstream tire. And so the clockwise moments would be equal to P2 times A times LP. And that would be equal to the counterclockwise restoring moment, which would be W times LW. W is equal to 1,500 kilograms times G, which is 10, which would be 15,000 newtons. And then what do I want to solve for? I guess I don't need to know that. I'm going to solve for that. So I'm going to solve for this. That's one thing we perhaps don't know. So W is equal to P2 times A times the lever arm, divided by the counter lever arm. And so this is equal to 5 times 10 to the 3 pascals times 3 meters squared times 1 meter, just making my life easy, divided by 1 meter. And I guess even I can do that math, but I don't need to because it's written here. 3 times 5 becomes 15. Times 10 to the 3, and it would be newtons. And this would be equal to 1,500 kilograms because of this. Bob's your uncle. That's it. And that's about the right weight of a truck, right? 3 tons, I think. 3,000 pounds. I guess that's 1.5 tons. Okay? And just since we have 2 minutes left, you can grab that, but I don't know if I did it. Did we lose it? So this is it. Be careful if you're on an apron wave in what you're doing. And so, yeah, so all we used was the fact that behind the jet engine. We know what the exit velocity is. We assume that that is the exit velocity right in front of the truck before it gets stopped by hitting it. And so we can use that velocity to convert all its energy into pressure energy, And if we know what that pressure is, we can resolve the forces around some failure geometry if we understand it. So that's it.